Okay. So, uh, okay. So last time we proved that if you have a solution to the harmonic Knapp's heat flow, uh, which is, in fact, we have just assumed it was, yeah, so yeah. So if we proved that if U is in fact just C21 M cross 0 T to N such that U satisfies, so we call this star, the harmonic Knapp's heat flow del U del T equal to tau of U, and U of x0 equal to f of x. So here this is on n cross 0 close 0 open T, and this is for all x in M, where f we're taking to be C2 plus alpha from M to N. Then there exists a constant C positive independent of T. C only depends on M, N, and F, such that the energy density is less than or equal to C for all xt in M cross 0T, and the norm of the time derivative del U del T is less than or equal to C for all xt in M cross 0T, right? We proved this. Yes? Okay.
Yeah.
Okay. So from this, using classical estimates for elliptic and parabolic PDEs, we can prove the following proposition, that there exists C. So C will denote different constants, okay, as usual. So C depending on M, N, F and alpha such that so here this energy density less than C means the first order space derivatives are bounded uniformly, and here the first order time derivatives are bounded. But actually we can say more, that if we look at the C2 plus alpha norm of u at time t, so this is a space norm, okay, plus the space norm of del u del t at time t, the C alpha space norm, okay, then this is bounded by this constant C for all t in 0 to open t, close 0, open t. All right. Okay. Is the statement clear?
Yes, sir.
So we're doing better than what we had last time. Now we're getting control over second derivatives. Okay. So let's prove this. So we view U as a map, U from M cross close 0 open T into RQ, taking values in the embedding of N into RQ, okay, which satisfies the nonlinear parabolic PDE del U del T equal to Laplacian U minus pi of U comma U of du comma du. Right? Yes. Okay. So then, first of all, for any t, if I look at the solution at time t, so the image of this is contained in the embedding of n, I of n, which is a compact subset of RQ. This is for all t. So since this is a compact, that means the solutions ut are uniformly bounded, right? Because they take values in a fixed bounded set. Okay. So we get that the C0 norm of ut, this is less than or equal to a constant only, let's call it C1, depending only on n, right? Okay.
Yes, sir.
Fine. So that's easy. Then we have that norm of the C0 norm of the energy of ut. This is bounded by a constant C depending on M, N, and F only. Right? This is what we proved. So this implies that the C1 norm of ut is bounded, right? Yes.
Yes, sir.
Okay. So look, I'll be using C to denote various different constants. So this C and this C are not the same constant. Okay. So the second constant will be larger than the first one. Okay. And now this implies that the C0 norm of pi of ut dut this is less than a constant C, right? Okay. Yes.
Yes, sir.
And finally, we have that the C0 norm of del u del t at time t this is less than a constant for all t. So putting these three together, what does this imply? 1, 2, and 3. Well, actually just 2 and 3. If I look at just 2 and 3, then these imply that the C0 norm of Laplacian ut so this is the C0 norm. So Laplacian ut I can write as del u del t plus pi of ut dut, right? So by 2 and 3, this is uniformly bounded. Okay. Right.
Yes, sir.
So now we can use the classical Schroeder estimate for elliptic PD. Which will give us that the C1 plus alpha norm. So any derivative of order less than or equal to 2 will actually be controlled by the C0 norms of just the Laplacian. So the Laplacian is a particular combination of second derivatives. The point is the C0 norm of the Laplacian actually controls the C2 norm of ut. Okay. So this will be less than some constant depending on m times the norm of Laplacian ut, C0 norm, plus the C0 norm of ut. Okay, this is the Schroeder estimate for elliptic PD. Okay. So this norm of Laplacian ut C0, this is bounded. for all t, and also norm of UTC0 is bounded. So the whole thing is less than some constant depending on m, n, and f, and alpha. This C depends on m and alpha. So okay. So is this all right? Yes. Okay. Yes. All right.
Yeah, it's
Fine. So what does this imply? This implies that if I look at pi of ut, dut, then this involves one derivative of ut, one space derivative. So if I take one space derivative, I get an alpha Holder function, right? Which is uniformly bounded because the C1 plus alpha norm of ut is bounded. That means the alpha Holder semi-norm of dut is uniformly bounded, right? So that will imply that the alpha Holder semi-norm of pi ut, dut, this will be uniformly bounded, right? Yes. Because this alpha Holder semi-norm of this pi ut, dut, that will be bounded as a function of the alpha Holder semi-norm of dut, right? And that is bounded by the C1 plus alpha norm of ut, which is bounded. Okay? Yes?
yeah.
Right?
Yeah.
So now this implies, yeah, go ahead. Any question? Okay. So this implies by the classical result on linear parabolic PD, we actually have this estimate, which is given in one of the textbooks for the course, the main textbook, Nishikawa's book, that the C2 alpha norm, C2 plus alpha norm of ut plus the C alpha norm of del u del t, del ut del t, C alpha norm. This is less than a constant times the SOP over, say, S in 0 to open T of Laplacian minus del del T of ut, the C alpha norm of this, plus the SOP over, so this should be a US, right? Well, what I mean is, this dot S. U at time S, and SOP over S in closed 0 open T. And similarly here, a SOP of just the C0 norm, US. Okay. Let me just check the notes. I think this is the correct estimate. Let me see. Yeah, that's right. Yeah. Okay. So this Laplacian minus del t applied to u, that is just pi of u comma du, pi of u of du comma du, right? So the whole thing is bounded by a constant depending on m and f and alpha. All right. Since Laplacian minus del t u prime s, this is equal to pi of us dus, right? Is this okay?
So is this like a Schauder estimate for parabolic PDEs?
Yes. The only thing is, this is not exactly the classical result that you find in most books. I looked this up. I could not find this exactly in the classical books of Ladizenskaya. But it seems this estimate is also true. So Nishikawa gives some references, but those don't exactly have this exact estimate. They have a slightly different estimate. So, okay, well, yeah. So, I mean, there you have to take a mixed norm of this the heat operator, this delta minus del t, this is called the heat operator. So you take the heat operator, say L applied to U, and then you have to take a mixed norm, C alpha comma alpha by 2. So that will bound this. And that plus the C0 norm of U will bound this.
Yeah.
Okay.
Okay.
So that's the classical Schroeder estimate. But actually, you don't need the time holder semi-norm. That is, you don't need to take a mixed holder norm, alpha comma alpha by 2. You can just take a space holder norm and then take the supremum over space. That seems to be enough. So that's all we have here. Okay, that's all we have here. So there's a slight, I mean, point to notice here. So, yeah. So, yeah. Okay. So using this, we can now prove. So with the same hypothesis as before, except assume moreover that f is, let's suppose f is C3, okay? So then f is in C2 plus alpha for all alpha, okay? Or C2 plus beta, if you like, for all beta. So then there exists ut, which is in C2 plus alpha, such that u little t converges to u capital T in C2 plus alpha as t increases to t, to capital T. Okay. And also del ut del t as a consequence, this converges to tau of u capital T in C alpha. as t tends to t. Okay. All right. So if our solution is defined on an open interval, I mean, half closed, half open, right? Then you have these UTs, they converge to some U capital T. So the limit exists. So that means your solutions don't blow up, right, in finite time. So this is like when you try to prove long-term existence of ODEs in Rn in finite dimensions. What do you try to show? You try to show that the solutions don't escape to infinity in finite time, right? Then you can define the solutions for all time. Yes, you've seen this argument before?
Yeah. So we start the initial problem again at
So
time t, right?
Exactly. Then you start the initial problem again at time capital T, and then you can extend the solution further, right? Exactly. So what we're going to do to prove long-term existence is take a maximal time of definition, right? Take the maximal interval on which you have a solution. Or rather, you'll have to take supremum of all times so that you have a solution. And then you'll get a closed, half open interval. Then you'll be able to extend to the endpoint. Then you restart the heat flow starting from this U capital T, and then you'll be able to extend a bit further. And that will give you a contradiction to maximality. Okay? Is it clear? That's the strategy we're going to follow. So it's just like the proof of long-term existence for ODEs. Okay, the harmonic maps heat flow, you can think of as an ODE, if you like, in an infinite dimensional space, right? In the Holder space. Okay. All right. Okay.
Yeah.
So, okay. So, so choose beta bigger than alpha such that 0 less than beta less than 1. So then by previous proposition, there exists C positive such that norm of del ut del t C beta, this is less than a constant C for all t in closed 0 open t. So that implies that the improper integral from 0 to capital T of norm del ut del t C beta dt, this is less than C times capital T, which is finite, right? So now C beta is a Banach space, right? The Holder space C beta is a Banach space. So in a Banach space, you know that an absolutely convergent series is convergent, right? Yes? Yeah, this is one of the basic theorems about Banach spaces. An absolutely convergent series is convergent, yes?
Yes, sir.
So similarly, an absolutely convergent integral is convergent. Okay, so you can define integrals in a Banach space as limits of Riemann sums. You can define the integral of a continuous function from an interval into the Banach space as a limit of Riemann sums. The same proof as in Rn will tell you that the limit of Riemann sums exist. And then you can, if you take an improper integral, then if the improper integral converges absolutely, that is the case here in the Banach space, then the improper integral will converge in the Banach space. Okay, so this implies that the improper integral so this is what we're going to be defining u sub t. This is defined to be f plus integral from 0 to t del ut del t dt. This converges in c beta. So when I'm doing this integral, I consider u as taking values in R cube, okay, via the embedding of n into R cube. So I can integrate because I'm taking values inside R cube. All right. Yes.
Yes, sir.
Okay. So this u sub capital T, a priori, this just belongs in C beta. Okay. But now, since alpha is less than beta, if you are bounded in C beta norms, then you will be pre-compact in C alpha norms. Okay. So the set u sub t, t in closed 0 open t, this is pre-compact. That means its closure is compact in C alpha. Okay. All right. So there's about 2 minutes left. Let me stop this session and we'll try and use the link which Orkut sent for the second session. All right. So let's use the link for the second session. Okay. Yeah. So well, there's 2 minutes left, but let me not rush it. Let me stop this session and we'll use the link for the second session. Okay. So I'll see you in the next session. Okay. I'm stopping this. Okay. All right. So, right. So we have alpha less than beta. So that implies if del ut del t is, well, if ut is, well, sorry, this is pre-compact in actually C2 plus alpha. Sorry. Because it is bounded in C2 plus beta. That's what we proved, right? In the previous proposition. Okay. Yeah. So that's because the inclusion of C2 plus beta into C2 plus alpha into C2 plus beta is compact. Sorry, the other way around. The inclusion of C2 plus beta into C2 plus alpha is compact. Sorry. That's what I meant to say. Yeah. Yeah. So something bounded in C2 plus beta will be compact in pre-compact in C2 plus alpha. Okay. So that implies there exists a sequence Tn, since this is compact, pre-compact, we have a limit point, right? As Tn tends to T, for some sequence Tn tending to T, and there exists G in C2 plus alpha such that UTN converges to G in C2 plus alpha. Okay. But then G of X, this is the limit n tending to infinity of UTN of X. And by the fundamental theorem of calculus, UTN of X I can write as f of x plus the integral from 0 to Tn of del u del t of x t dt, right? And this converges to, since the improper integral converges, this converges to fx plus integral 0 to t of del u del t of xt dt. And this is equal to u sub capital T of x, right? So that implies that u sub capital T is identically equal to G. So thus, u sub capital T belongs to C2 plus alpha, right? Okay. Is this all right? Yes? Yes, is this
Yes,
okay?
sir.
Yeah, okay. And this shows that the only limit point of the set u sub t, t in closed 0 open t, is u sub capital T. So the only limit point of this in C2 plus alpha, so in C2 plus alpha is u sub capital T. Hence the whole family converges to u sub t, capital T. Okay. So hence u sub little t converges to u sub capital T in C2 plus alpha. Right, because it's a pre-compact family with a unique limit point. Therefore, the limit exists, right? Is that clear? Yes?
Yes, yes.
Okay. So hence, since this converges in C2 plus alpha, that means tau of ut, this converges to tau of u capital T in C alpha, right? But this tau of u little t, this is equal to del u del t. Okay? By the heat flow equation, right? Okay, so that was the other thing that we wanted to prove. Okay, so this proves the proposition. Is this okay? Yes?
Yes, sir.
Okay. So now we can prove the theorem that suppose so long-term existence So let Mn be closed Riemannian manifolds and suppose that N has non-positive sectional curvature. Okay. So then for all F from M to N, say C3 map, for all alpha in between 0 and 1, there exists a unique U from M cross 0 infinity to N such that U belongs to C2 plus alpha 1 plus alpha by 2. Yeah, actually, I have a little problem with this. Yeah. Okay, maybe let me just let me make F smooth. So smooth map, and then U is actually going to be smooth from M cross 0 infinity to N such that it solves the heat flow with initial condition F. Okay, so right, yeah, let me see. Okay, so proof. So let T naught be, first of all, the supremum of capital T positive such that there exists U which is C21 M cross close 0 close T to N solving the initial value problem star. Okay. Yeah. So note if U1 belongs to C21 M cross close 0 T1 to N and U2 belongs to C21 M cross close 0 T2 to N. So if these are solutions of star, so then U1 is identically equal to U2 on M cross 0 up to the minimum of T1 and T2, right? By uniqueness of solutions. Yes?
Yes.
That we already. So what does this mean? This means that if we look at all these solutions defined on intervals 0 to t, then all of them agree wherever their domains intersect, right? So therefore, we can obtain a solution on M cross closed 0 open T naught, right? On this maximal interval, we can get a solution on close 0 to open T naught. Is this clear? Because if I take any time, say strictly less than T naught, say T naught minus epsilon, then because T naught is the supremum, I can always find a capital T which is bigger than T naught minus epsilon, where I have a solution, right? So then I define my U to be that solution. Now this is well defined because if I have any other solution also defined on up to T naught minus epsilon, then the two solutions agree up to T naught minus epsilon, right? So therefore, this is well defined. Is this clear?
Yeah, it's clear.
Yes?
Yeah.
Okay. Now we know. Now we know there exists ut naught, which is in C2 plus alpha such that u little t converges to ut naught in C2 plus alpha as t increases to t naught, and del ut del t converges to tau ut naught in C alpha as t increases to t naught. Okay. So since ut naught belongs to C2 plus alpha, by short-term existence of solutions to the harmonic maps heat flow, there exists a solution V which is in C2 1 M cross closed 0 to epsilon n such that del V del T is tau of V, and V at time 0 is equal to ut naught at time 0, right? Okay. So this is what you were saying. We restart the heat flow at starting from ut naught, right? Restart it at time t naught. Okay. So then define U from M cross close 0 to T naught plus epsilon to N by U of xt. So let me call this U tilde. Okay. So U tilde of xt is equal to u of xt, my original solution, if t belongs to close 0, open t naught, and define it to be v of t minus t naught, x comma t minus t naught, if t belongs to t naught to t naught plus epsilon. All right. So let me make this closed. Okay. Yes.
Yes, yes.
So all we have to check is that u is in C2, 1, right? So the second space derivatives are continuous, right? So we just need to check continuity as t tends to t naught, right? If t is less than t naught, then this is in C2, 1. And if t is bigger than capital T naught, this is in C2, 1. The issue is continuity at t naught, right? So the point is that u tilde t, this is equal to u sub t if t is less than t naught, and this converges to u sub t naught, which is u tilde t naught, right? If so, this converges in C2, right? So that implies that space derivatives of u tilde of order 2 are continuous, right? Of order up to 2 are continuous. Is this okay? Yes?
Yeah, yeah.
And if similarly, if I look at del u tilde del t, this is equal to del ut del t if t is less than t naught. And this converges to how should I put it? Well, this converges to tau of ut naught, right? Which is tau of u tilde t naught in, well, this converges in C alpha, so also in C0. So that implies that the first time derivative of u tilde is continuous. All right? Yes? So thus u tilde belongs to C2, 1 m cross close 0 to close t naught plus epsilon n satisfies star, and that's a contradiction since t naught plus epsilon is bigger than t naught. Okay. So contradiction by definition of T naught. Is this all right?
Yes, yes.
Okay. So yeah, the last thing to say is actually, yeah, so what the last thing to say is that now the yeah, so now if I look at Laplacian minus del t of u tilde, this is pi of u tilde du tilde du tilde so this belongs to C 1 comma 1 because I've taken one space derivative, right? But I'll still have one time derivative and I'll still have one space derivative. So this implies by a classical result that actually u tilde will gain two space derivatives and one time derivative. So it will belong to u 3 comma 2. Okay. And that will imply that pi of u tilde du tilde this will belong to C 2 comma 1, sorry, 2 comma 2. Yeah, 2 comma 2. And that will imply that again iterating u tilde will belong to, so you'll gain two space derivatives. So C 5 comma, and you'll gain 5 comma 3 and so on. Okay, so iterating, we'll get that u tilde belongs to C, what will it be? 2k minus 1 comma k for all k. Greater than or equal to 1. So, yeah. So, and so u is u tilde is C infinity. Okay. Okay. So this is from the classical result that if the heat operator applied to a function belongs to some C m comma n, then the function itself gains two space derivatives and one time derivative. And also there are some mixed derivatives in this mixed CK space. So actually you will have all mixed derivatives. As k tends to infinity, you will get all mixed derivatives as well. So this will be C infinity. Okay. All right.
Yeah. I just have one question. Can you scroll up?
Yes,
Before
sure.
before this long-term existence thing, just
I see. I see. Okay, okay. Yeah.
here, you're saying that del U del T tends to tension field of U capital T. How did you get that?
Because the tension field of U little t, this is a combination of second derivatives, right?
Yeah, yeah.
So uh, because U little t converges to U capital T in C2 plus alpha, that means if I take any second derivative, that will converge in C alpha, right?
Yeah, yeah, okay, okay. So no, so you here from here you no, here you are using that del U del T is converges to del U capital T. I mean,
No, 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 no,
derivative of cap.
no, 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 no. See, I'm just
No, no,
using
to
that
get
term.
the heat flow thing right. I mean, to
No,
show
no,
that it satisfies the heat flow at time T. I mean,
no,
no, you're
no,
not
no,
assuming,
no,
but
no, 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 no. No, 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 you're misunderstanding. This UT converges to U capital T, right? In C2 plus alpha.
Yeah.
Okay?
yes,
Yes? So therefore, if I take any second derivative of UT, that will converge to U, the same second derivative of
yeah,
U
but that
capital
is
T.
space derivative, right?
It's yeah, wait. Yeah, space derivative. Yeah, this is a space derivative only is converging. Yeah. So I'm just saying the space, this is converging in space semi-norm, in space norm. Del U del T is converging in space norm to this, right?
Yeah, yeah. No, what I'm asking is that the time derivative of at T converges to time derivative of at capital T, right? You are
No, no, we don't have a time derivative at capital T a priori. A
okay.
priori, we don't have capital time.
Okay, okay.
Time. We only have the tension field at time T, capital T,
Hmm.
right?
Okay, yeah, yeah.
So
Fine.
what I'm saying is the time derivative converges to some value at capital T. Okay.
Okay, okay, fine.
Now this will imply that the time derivative at capital T exists. Okay, but that will follow from the classical theorem. This is an infinite dimensional version that if you have a function, if f prime is defined on, say, close 0 open T, and f prime T converges to C as T tends to T, right? Then f is C1 on the whole interval 0 to close 0, close T, right?
Okay.
This is just
Hmm.
like first year
Yeah,
real
yeah.
analysis, yes? Right? So a version of that will give you that this is differentiable at capital in time at capital T as well.
Yeah, yeah. Okay.
Okay. But we don't have the time
Yes,
derivative a
yes, yes.
priori, right?
Yeah, yeah.
We don't have.
Thank you.
Okay. All right. Okay, so that gives long-term existence of the heat flow. And using this, we can actually prove the Eel-Sampson theorem. So let me give that proof now. So just for completeness. So theorem. So this is, if you like, the main theorem of this course. This was the main goal of this course, is to prove this theorem. So let M and N be closed Riemannian manifolds. Such that the sectional curvature of N is non-positive. Then any continuous map F from M to N is homotopic to a harmonic map U from M to N. Okay. Let me call it U infinity from M to N. Okay, so what's the proof? The proof is, so first by a classical result, F is homotopic to a smooth map F naught from M to N. Okay. So now once you start with a smooth map, then you can run the harmonic map seed flow for all time, right? So then there exists U from M cross 0 infinity to N C infinity solution of harmonic maps heat flow starting from F naught. So that means U naught is equal to F naught. Okay. So then for any alpha in between 0 and 1, we know that the set ut t in 0 infinity this is bounded in C2 plus alpha, right? Okay, there's less than a minute left. Let me stop this and start a new session. Okay. So we'll join using the link for the third session. Okay, the link for the third session. So I'll stop this now. Okay. Yeah. So we're proving the Eel-Sampson theorem that if M and N are closed Riemannian manifolds, where N has non-positive sectional curvature, then any continuous map F from M to N is homotopic to a harmonic map U infinity from M to N, right? So by a classical result, we know that F is homotopic to a smooth map F naught from M to N. Then since F naught is smooth, we can run the harmonic maps heat flow starting from F naught, right? So we'll get a solution on M cross 0 infinity, say U, okay, such that U naught is F naught. Now, if I take any alpha in between 0 and 1, then we know that we've already shown that the C2 plus alpha norms, space norms of the solutions are uniformly bounded in for all time, right? So this means that this set is pre-compact in C2, right? Since if you are bounded in C2 plus alpha, you will be pre-compact in C2, all right? Okay, so thus, since this is pre-compact in C2, there exists a limit U infinity in C2, and there exists a sequence Tn tending to infinity such that UTN converges to U infinity in C2 as t tends to infinity, right? As Tn tends to infinity. Yes? Okay. And then we showed by a previous result tau of u infinity is 0. Yeah, this we showed when we started in the beginning talking about the harmonic maps heat flow. This is the first thing that we showed, that if we have a solution of the heat flow defined for all time, and if it converges in C2 norm as along some sequence, Tn tending to infinity, then the limit of that sequence must be harmonic, right? Okay, so tau of u infinity is 0, and this implies by previous result that u infinity is smooth and harmonic, right? Yes, this we already showed. Okay.
Yes.
Yes. Yeah. And now we use a fact that this will show also. There exists epsilon n. So an epsilon depending on n. So I'll call it epsilon n, such that if G and H are maps from M to N, such that the distance between G and H, that means the sup of x in M, D, Gx, Hx, if this is less than epsilon n, then G and H are homotopic. Okay. So if two maps are uniformly close enough, then they are homotopic. So we'll prove this in a little bit. So it follows that thus UTN is homotopic to U infinity for n large, because UTN converges to U infinity uniformly. So thus we're done, right? F is homotopic to F naught, which is U naught. And by continuity of the solution, U naught is homotopic to UTN, right? And UTN is homotopic to U infinity. So that's it. All right. Okay. All right. Is this all right?
Sir.
Yeah.
Yes. Okay. Yes. Okay.
Yes.
So, any question? So, what we're doing is inside maps from M to N, C0 of M comma N, we start with some F. We homotop it a little bit to some F0, which is smooth. Then we run the harmonic maps heat flow to some, so F0 is U0. Then you run the heat flow to some UTN. This is close to a harmonic map U infinity. So these two are also homotopic. So that's it. Okay. So you get a continuous path in the space of maps. That means a homotopy, right? Is it clear?
Yeah, yeah.
Yes?
So I just have one question. You use that U is bounded in C2 plus alpha. So initially we got that
Yes.
bound only till a finite time, but I mean, it's just as we like started the IVP at some time t, then I mean we can extend
No,
it to
no,
any
no,
other
no,
time.
no, 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 no,
Oh,
no,
no.
no. That bound is valid for any capital T, right? Look, I'll show you again.
Okay. On whenever it is defined.
Yes. So let me show you. Yeah, this proposition. So why is it not going up? Okay, 1 second. Yeah, so yeah. So here there exists a constant which only depends on M, N, F, and alpha. It does not depend on capital T.
Yeah, yeah. Okay.
It does not depend on the time of existence. So I can take T as large as I want. If it's defined on the interval 0 infinity, I can take T as large as I
Yeah,
want, right?
all right.
So this bound will hold on all of 0
Yeah.
infinity.
Hmm. Yeah.
Okay.
Thank you.
Is it correct? Yeah. Yeah. This C does not depend on capital T. That's the whole point, right? That's why we can extend solutions up to time capital T. No, because the bound does not.
Depend on T.
Yeah. So it does not. Yeah. It's independent of time. Yeah. So, yeah. Okay. Okay. Any more questions? Okay. So good. This proves the Eel-Sampson theorem. So, for example, we can look at some applications. So, one application we already did is that if n is closed and the sectional curvature is non-positive, then all the higher homotopy groups vanish, right? Pi k of n is 0 for all k greater than or equal to 2, right? Yes? And the proof is because any continuous map f from the k sphere sk to n is homotopic to a harmonic map u infinity from the k sphere to n, and the Ricci curvature of the sphere is strictly positive and sectional curvature of n non-positive. This implies that u infinity is constant, right? This we proved much earlier. Yes? Yeah. Yes?
Yeah, yeah.
Okay, so therefore f is homotopic to a constant. So that means the higher homotopy group is trivial. Okay. Yes? Is this
Yes,
okay?
sir.
Okay. So as another application, if n is closed and suppose the sectional curvature is strictly negative, okay, then we can show the following. Then proposition. So I think I gave this as an exercise in the assignment. For any elements of the fundamental group alpha beta in say pi 1 n say q if alpha beta commute then there exists gamma in pi 1 and q such that alpha and beta are both powers of gamma. So in other words, they belong to the cyclic subgroup generated by gamma. Okay. All right. Okay. Is the statement clear?
Yes, sir. Yes, sir.
Yeah.
So actually you would have seen an example of this in hyperbolic geometry. So suppose n is equal to the, say, hyperbolic plane quotiented by a discrete group, right? Gamma. So gamma is co-compact. Co-compact, fixed point free. Fixed point free. And discrete group of isometries. Of H2, orientation preserving isometries. Okay. So for example, so then the sectional curvature of n is constant equal to -1. Okay. So it satisfies the hypothesis of the proposition. It's negatively curved. Yeah. So for example, if you take the disk model of H2, yeah, then you would get a picture like this. Yeah, the genus 2 surface would be the quotient of H2 by the group gamma. And you can get this by identifying sides of a fundamental domain, which would be a hyperbolic octagon, right? So 1, 2, 3, 4, 1, 2, 3, 4, right? And you would identify these sides, these sides, these sides, and these sides, okay? To get these sides will give you these loops. All right. Like this, yeah. Okay. So you get this as a quotient of a, in general, a 4G-gon, right? This picture you've seen, yes? So elements of the fundamental group is identified with the group of deck transformations gamma, right? So this is the group of deck transformations. And in this case, any gamma in gamma, which is not identity, is what's called a hyperbolic element. Is a hyperbolic isometry of H2. So hyperbolic isometry means that It's going to be a Mobius map which has two fixed points on the boundary. Okay, one is an attracting fixed point, gamma plus, and the other is a repelling fixed point. And there is a hyperbolic geodesic, which is an arc of a circle perpendicular to the boundary, such that along this geodesic, gamma acts as a translation, right? And this geodesic, it projects to a closed geodesic below. All right. It projects to a closed geodesic below. So the length of this closed geodesic, that is the amount by which you translate here. Okay, this is the picture. All right. Yeah, so these 2 points get identified on this geodesic to give you a circle below. All right. Yes.
Yeah.
Okay. Now, if I have two fellows which commute, so if they commute, then their fixed points have to be the same. So if they commute, you can't have a picture like this. So say this is alpha plus, alpha minus, and this is beta plus, beta minus, right? Because if they commute, you see what are the fixed points of the conjugate? The fixed points of alpha, beta, alpha inverse. This is alpha of the fixed points of beta, right? Yes? Yes?
Yes.
And if they commute, then this conjugate is the same as beta. So that means that alpha preserves the set of fixed points of beta. But the only set which is invariant under alpha is this 2-point set alpha plus, alpha minus. Okay, because all other points along the boundary, they move like this. They move towards the attracting fixed point and away from the repelling fixed point. All right. So there is no other subset of the boundary which is invariant under alpha. So if it's an invariant subset, it must be equal to this 2-point set, alpha plus, alpha minus. All right. Okay. So that implies that beta plus, beta minus is equal to alpha plus, alpha minus. All right. Yes. Yes. All right. Okay. And that implies that if I so there is a one parameter group. So there is a one parameter group of translations which preserve this geodesic. Okay. So there is a one parameter family of hyperbolic. There's a one parameter group subgroup of hyperbolic isometries which translate along this geodesic. All right. So so that means that the subgroup generated by alpha and beta, this is a discrete subgroup because it's a subgroup of the whole fundamental group which is discrete. This is a discrete subgroup of a group gamma T in R. Okay. And since it's a discrete subgroup of, so this is isomorphic to R, since it's a discrete subgroup of R, it has to be cyclic, right? Yes?
Yes.
Yeah, so that implies that is cyclic. Okay, so that's the proof if you take a hyperbolic surface. But the point is, this holds in general. for a general closed Riemannian manifold. So that means in particular, it holds in higher dimensions, not just H2 in 2 dimensions, but moreover, it holds for manifolds of variable negative curvature, not necessarily constant curvature, right? Okay. So this holds in variable negative curvature. And so the proof of the proposition, let's finish with this today. So let's see how to do this. Okay. So we have that if alpha beta commute, so that implies that the loop, how to write it? So let's read it like this: alpha dot beta dot alpha bar dot beta bar. This is homotopic to a constant, right? Yes. Yeah, that's what it means for alpha beta to commute in the fundamental group. Yes.
Yes, yes.
Okay. Now this is a loop. So this is homotopic to a constant. So now a loop is what? It's a map from S1, right? To the space. Yeah. So you'll have, let's say, so alpha, beta, and then alpha bar, beta bar, and you can, so there is a one parameter family of curves, right? So we have a homotopy. Let me call it, say, I don't want to use gamma, so say delta sub t. These are maps from S1 into N, right? Such that, say, delta 0 is constant, Q, and so this Q is the starting point. So this loop is alpha, this loop is beta, and delta 1 is equal to alpha, beta, alpha bar, beta bar, right? Yes? Okay. So this is our homotopy. Yes?
Yes, yes.
So this homotopy actually will give a continuous map from the closed disk into the manifold, right? So we get a map phi from the closed disk into N, right?
Yes.
Because restricted to each circle of radius t, you let it be delta t. Do you understand?
Yeah, quotient S1 cross I, right?
Yeah, so at the origin, this is well defined. This is continuous at the origin because delta 0 is a constant, right? So as the circles shrink, you get a continuous map. Is this okay?
Yes, sir.
Yeah, so phi of t e to the I theta is equal to delta t of e to the I theta. All right, that's the map. Is it clear?
Yes.
Okay. So this gives a continuous map from the closed disk to N. Now what we can do is, so this closed disk, I can divide into 4 equal segments which map to alpha, beta, alpha bar, beta bar, right? Okay, so here this maps to alpha. This maps to beta. Well, okay, maybe which way do we go around the circle? Anti-clockwise, right? So yeah, this way. So this maps to beta. This maps to alpha bar, and this maps to beta bar, right? Okay. Yeah. We can do this. Yes. Right.
Yes, sir.
Okay. And we can assume that so yeah, so then what we can do is so see this a point here. Oh shoot, sorry. Use the wrong thing. Oh, what am I doing? What is this? Yeah, okay. Yeah, sorry. Okay, so yeah, so a point here will map to some point on alpha, and some symmetric point will also map to the same point here, right? Okay. So what does that mean? That means there are points on this arc and this arc, right, which map to the same point here. So what I can do is I can quotient this disk by identifying the boundary sides like this, right? So if I identify the boundary sides, what do I get? I get a torus, right? It's a square with opposite sides identified, right? Topologically. Yes?
Yes, sir.
So this quotients to a torus. Okay. This is M, which is R2 mod Z2. And so this phi induces a map from the quotient, right? Phi bar. So let me call this F. This goes from M to N, right? This is a continuous map. Yes?
Yes, yes.
All right. Yeah. Such that this maps the generators, F maps the usual generators. So the generators of the fundamental group are the horizontal and vertical circles. So it maps generators of pi 1 M to alpha and beta, right? Okay. Yes,
Yes, sir.
that's how we've constructed it. Yeah. So now what? Now since the sectional curvature of the torus is 0, right? So that implies the Ricci curvature of the torus is 0, right? The sectional curvature is 0 because locally it's isometric to R2, right? Which is flat, which has 0 curvature. Yes?
Yes, yes.
So sectional curvature of the torus is 0. So the Ricci curvature is 0. And the sectional curvature of N is negative. In this situation, we know that if F is homotopic to some harmonic map U infinity, from the torus to n, then either u infinity is constant right? Or we showed that u infinity of n is equal to gamma, a closed geodesic. So let me call it gamma naught, a closed geodesic in n, right? Yes?
Yes, yes.
Yes, sir.
So if u infinity is constant, then we're done, right? So because then f is homotopic to a constant. So that implies that alpha and beta are both 0, right? I mean, identity. Okay. So we're done. Right. Otherwise, alpha and beta, they're in the image of f, right? So they must be multiples of this gamma naught. So not exactly gamma naught. What happens is that, so the only issue is about base points, because here we're looking at free homotopies. So alpha and beta will be freely homotopic to multiples of gamma naught, right? Yes? So maybe I should write that here. So yeah, so otherwise, so alpha, beta, freely homotopic, right, to gamma naught power m, gamma naught power n, right, for some mn. Yes?
Yes, sir.
Because the image of u infinity is inside gamma naught and f is homotopic to u infinity, right? So then we're more or less done. The only point is that, see, the base point could be somewhere here, and gamma infinity may not pass, gamma naught may not pass through the base point, but you can do the usual thing. You just choose a curve delta to from q to the starting point of gamma naught, and then you define a loop at q, gamma, which is, so you go by delta and then gamma naught and then delta bar, right? Okay. So this will be an element of pi 1 nq. Fine. So then alpha is gamma power m and beta is gamma power n. So we're done. All right. Is this clear?
Yes, sir.
Okay, that's it. Is this all right?
Sir,
Yes, sir. Yes.
Yes.
all the homotopies we are taking fixing the base point q or
No, no, no. Actually, this delta is the image of q under the free homotopy.
okay.
From, yeah. So actually that will be the free homotopy from f to u naught, u infinity, right?
Okay.
It's the image of, yeah, q under the homotopy from f to u infinity. That's what it is. Okay. Is it clear?
Yes.
Okay, that's it. So that's it. So so finally you can show that any abelian subgroup of the fundamental group has to be cyclic. Okay, so next week and there are just 3 classes left. We'll spend it doing problems, all right? Maybe I might do a little bit more theory, but mainly we'll do problems, okay? The problems in the assignment, all right?
Yes, sir. Yes.
Okay? Okay, all right. So see you Tuesday.
So I
then.
think, hello, sir. I mean,
Yes, yes.
the problem that you just did, I
The
think,
time's out. Almost done.
it's in the assignment, right?
Yes, 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 yes. Yes. Okay, all right. So see you Tuesday.